Hi, I'm Ole Kröger, and today I want to present you ConstraintSolver.jl, a project learning by doing. About 2 years ago, I had the idea to write a Sudoku solver in Julia, something similar I've written in Python before, and I wanted to see the speed of Julia. And then from the Sudoku solver, I went quickly into just writing a complete constraint solver on my own, which is a very long project. And there's more to come, but more on that at the end of this presentation. So first of all, let me explain what a constraint solver is. So on the left-hand side, you see a standard mathematical optimization problem. Most of you are probably familiar with it. We have a function f that we want to minimize, and f here depends on two types of variables, x and y, where x are continuous variables and y are discrete variables. And we have some constraints here, g, on that variables as well. Here they have to be smaller or equal to 0, so some kinds of constraints like 2x plus 2x1 plus 3y1 smaller or equal to 0, these kind of things. And maybe they have to be linear or non-linear. Those are normally more, these can be more specified later. Now on the right hand side, you can see a Sudoku puzzle, and it's not like immediate obvious of how you want to solve it using the standard mathematical optimization model. So normally, let's assume we have the Sudoku or a scheduling problem or some other real-world problem. It's not always super intuitive to write this in the normal mathematical language, as you've seen before. Often needs some kind of abstraction, so it's not like directly what we would express to another human being, for example. And it often involves the classification into, is it a linear problem? Is it a non-linear problem? Do I have only continuous variables or do I have discrete variables? So the idea of a constraint programming solver is to have a broader description language. So you can say these values have to be different from one another, or 2x plus 3y is not equal to 7, something that is not linear, and also non-linear solvers normally don't have this option. Or things like is bigger than instead of bigger or equal to. And the idea is that it's very easy to just write new constraints that can be problem specific and just provide a standard system of how to add new constraints, but also some standard constraints that are very useful in general. And a list of those you will see at the end as well. And then the idea is that the constraints are very independent of each other, but more on that also on a later slide. Now let's talk a little bit more about the differences in solving discrete problems. First, we have a look at the standard mathematical optimization. So because my constraint solver only works with discrete variables. But normally you solve a relaxed or continuous version first, here denoted as the root node. And then, for example, you have variables y1 and y2. And in the first case, y1 in the relaxed solution, let's say it's 0.5, but it's not discrete. So we split it up into two parts, one where we set y1 has to be smaller or equal to 0, and another one where y1 has to be greater or equal to 1. So we remove the solution that's actually not possible because it's not discrete, and now we have two problems that we have to deal with. And then we basically do the same thing for y2 again. Maybe this one is set to 0.75 or something. And we just reiterate that. So now let's have a look at the constraint solver approach. As mentioned before, I only work with discrete variables, and the idea is to directly remove impossible values from the search space, which is called pruning. So we have the root node, we prune, as you will see in a second on the Sudoku. Then you might select a variable once where pruning is not longer feasible, or you can't prune anything anymore. You set a value then, or remove the value from the possible values here of x. And this way you do your branching. So you try out a discrete value or you remove it. And then you reiterate here, for example, for variable y. And maybe you have to backtrack from time to time until you find a feasible or optimal solution, depending on whether you have a feasibility problem or an optimization problem. Now, here we see the Sudoku from before, but basically we've written down what kind of values are directly not possible for each cell. So at the upper left-hand corner, you can see that only the values 1 and 8 are possible because 2 and 3 are already removed from the 3x3 block. 4, 5, 6, and 9 are removed because of the row, and 7 is removed because of the column. And now we can also, in the second block, so here we can fix the 1, we can remove the 1 from the row, the column, and the block. And now we could fix the 8 and so on and so forth. And in a lot of cases, it's not really needed to use backtracking at all when we solve Sudokus. It's more needed for more difficult problems. And this is just directly removing what's obvious, which is not possible. But actually the constraint solver uses something more sophisticated to remove more values. But I don't want to go into detail on that. I created a YouTube video about that, so let me know if you have any questions on that. Now let's have a look at the code for expressing a Sudoku puzzle. Here we create a 9x9 grid of variables called x, and we have a grid which just have the predefined values set, and otherwise it's 0. So when it's not 0, we fix the variables, and then we have 3 constraints. They are all different constraints. So basically how you actually would like formulate the rules of Sudoku to another human being. And then we just say this all different is for the rows, for the columns, and for the blocks. Now, why did I start with ConstraintSolver.jl? As mentioned before, I just wanted to write a Sudoku solver, basically get a little bit more familiar with Julia and with constraint programming for that matter. And in September 2019, there was no constraint solver available in Julia yet. So I thought, okay, let's write my own, which can't be that hard, right? Okay, well, it's a long project, and it will be there for much longer to come, but I'm learning a lot of stuff. Anyway, I had some experience with Julia and with jump and MathOpt interface as I created the mixed integer nonlinear programming solver Juniper.jl a couple of years prior. Now, I also wanted to test the boundaries of the extendability of jump and MathOpt interface because they are intended for the normal mathematical programming models, but not so much for constraint programming. And I also wanted to learn and also teach about constraint programming. And therefore, I decided to write whatever I implement in the constraint solver. I write a blog post about that. And currently, there are more than 30 posts about the project on my blog, opensource.as. So that was like why I wanted to do it. Let's have a look at how it actually works. So let's assume we only have two variables, v1 and v2, and we have three constraints. Here c1, c2, and c3 on the left-hand side. The variables have the discrete values 1 to 5 given, and now we can apply the first constraint and remove value 1 because it has to be greater or equal to 2. And let's apply the third constraint here. The value 2 has to be greater than the value 1. So we can actually remove the 5 from value 1, from variable 1, sorry, and we can remove 1 and 2 from variable 2. Now, when we apply the second constraint, it says variable 2 has to be smaller or equal to 3, so it's actually fixed now. And because variable 2 changed, we already went through all the three constraints, but because variable 2 changed now, we actually can apply the third constraint just again. And when we do that, both variables are actually fixed. So here we fixed variable 1 because it has to be smaller than variable 2, which was already fixed. So we have now a feasible solution, and it's actually the only solution as we didn't do any backtracking. Now let's have a look at another problem. It's the 8 queens problem. So we want to find a solution. So we want to place 8 queens on a chessboard, on the regular 8x8 chessboard, such that they can't see each other basically, or capture each other if they would be of different color. And you can see here a backtracking approach and as well as a pruning approach. So all the red value or the red squares are impossible because there's already a queen which sees these squares. And in blue, I've marked the queen that was placed at the last step. And if there are queens, other queens maybe on the board, which haven't been set before, those have to be set based on the queens that are already on the board. And you can see that we can find such a solution. That's actually because I said I just want to have a feasible solution and just show one solution here. And you can see the backtracking approach that was taken. Now, how is working with Julia? So working with Julia is especially nice because of the multiple dispatch functionality. So I use a very similar approach to what MathOpt-Interface does as well. So here I use different functionalities, for example, initializing a constraint or pruning a constraint, and they depend on the constraint type, the function type, and the set type. So as you maybe remember the constraints in the Sudoku, where these variables are in the set of all different variables, which is this function are just a vector of variables, and the set is the all different set, or here an internal version of that. And it's also possible to use automatic differentiation, which was tested before, but I don't want to go into detail on that. And it's possible to specialize on integer problems, so when not only the variables have to be discrete, but also all coefficients of maybe, for example, linear constraints are discrete. Then everything can be specialized to integer problems, which is possible with MathOpt-Interface, but not with JUMP at the moment. Now, talked about Julia, let's talk a little bit more specific about JUMP and MathOpt-Interface, or MOI. It's relatively simple to just create a new solver interface. It's easy to define which constraints are supported and which aren't. So for example, here on the right-hand side, you see that the optimizer that I created supports vector variables in all different set constraints. Also, we'll talk a little bit about adding new constraints, and it's very easy to like create this simple function in set structure for like they all different constraint, but it's also possible to create completely new constraint types, like the one you see here. So for example, I created a reified constraint, which is similar to the indicator constraint, which is already implemented in JUMP and MOI. I created AND, OR, XOR, and complement constraints. And you can see that it involves just basically new methods for parse constraint head and parse one operator constraint. But yeah, that's nothing that I want to like show completely on this talk. And on the right-hand side, I've created kind of a new constraint type, which depends on creating new variables and new constraints, which is the all different except 0. So we have some variables x, a vector of variables x, and they have to be all different from each other, or they have to be 0. So with the reified constraints, which is like the first constraint, I can set that the anonymous variable b is set to 1 if both of them are if both of them, so xi and xj, are not equal to 0. So here you have the reified constraint and the end constraint combined. And if that is the case, so if both are not 0, they have to be different, as stated by the constraints. And another very useful thing that is provided by JUMP and Math-Opt interface is called bridges. So what are bridges? Bridges are transformations of one constraint into one or more other constraints. So we will have a look at the example in a second. And the reason is basically the solver doesn't need to support all kinds of different constraints if there is an easy transformation between them anyway. So here we have the example 2x plus 3y smaller equal to 7. And let's assume that the solver only supports the equal constraints in creating new variables. And then we can create a slack variable z, and z has to be greater or equal to 0. And then we have the constraint 2x plus 3y plus z equals to 7. And I use that, for example, I only support less than or equal constraints, but not greater or equal constraints. But if you flip all the signs, it's the same thing. So I use a bridge for that. Now, something that's not done much before is what I call bridgeception, which means we allow default bridges as well as new bridges that I've created inside indicator, reified constraints, and Boolean constraints. So in the code example below, you see, for example, that I write the greater constraint, which the constraint solver doesn't support directly. I only support the less than constraints, and it's inside an AND constraints or several AND constraints which are nested, and those are inside an indicator constraint. So with this bridgeception, it's possible to just flip the signs everywhere, but have everything inside all the AND constraints as well as inside the indicator constraint. Now, as mentioned at the very beginning, there haven't been any constraint solver progress before September 2019, but actually now there are several projects and other people who are working on constraint programming in Julia. And there's also another talk by Jean-François Baffier in this conference. So maybe it was already or it will be held. Please check that out as well. And there's also constraint programming extensions, which is a project which creates new constraint types, which then make it easier to support inside new kinds of solvers, such that not every solver developer has to implement the new constraint types to extend jump and method interface. And the local search solvers project is part of the Julia Constraints organization, which is also new. And maybe one day the ConstraintSolver.jl project that I'm working on will also be part of that organization. So I'm looking forward to a bright future of constraint programming in Julia. Now, at the very end, I want to talk a little bit about the timeline, so what I've already accomplished with ConstraintSolver.jl, as well as my ideas for the future. So here on the left, you see that it started in April 2020. As mentioned before, I actually started September 2019, but I released the first version 0.1 with the all different constraints and basic linear constraints in April 2020. Later that month, I created a table constraint, which is also very useful, where you can just specify possible solutions for one variable. So they have to, for example, they have to be odd, or they have to, I don't know, be squares, or things like that are very easy to express with the table constraint. Now, in June that year, I implemented the indicator constraint as well as the reified constraint. And then I worked a little bit more on performance for faster graph coloring, for better pruning of reified linear constraints. So for example, if it's 2x plus 3y is smaller or equal to 7, as we've seen before, but actually because of the reified constraint, the first part, the activator is deactivated, then we can prune the complement constraints. So that provides better pruning functionality. Also worked on a different search method, which is used for the branch and bound parts, called activity-based search. I want to add more in the future, but more on that in a second. Then earlier this year, I created and or constraints, and just recently I created XOR and XNOR constraints. Using the XNOR is using the complement sign of the XOR. And now the outlook for the next parts of the constraint solver journey that I want to do is to support element constraints. Already started with it. I just need to implement them in indicator and reified constraints. I want to support more different branching strategies and maybe also a possibility such that the user easily can say what variables it's more useful to branch on, because sometimes there's insider knowledge from the user. I want to implement the scheduling constraints, which need some work on jump and method interface before. And I want to go into parallel pruning, which I think will be a strong point of Julia in constraint programming, as it's very easy in Julia to work with different threads. So yeah, that's the current goal for this ConstraintSolver.jl project. If you're interested, please check out my blog, as well as the project itself, of course, and I'm looking forward to your questions. Thanks, everyone.